morning. I am Arpit. I handle technical operations at the PEER-UC Berkeley facilities, lab facilities located in Richmond Fuel Station. To begin with, PEER oversees operation of two labs located in the Richmond Fuel Station facility under UC Berkeley. The first one being the earthquake simulator lab, which is pictured right here, which is also the shaking table. And we also oversee operation of a different lab for structural testing, dynamic and pseudodynamic and static testing. To begin with, here is a picture of the lab, the shaking table looking all clean. This is a picture from last year, the 50th anniversary of the table, so it is an old facility. We had quite a bit of a crowd. To give an overview of the table itself is a 20 feet by 20 feet platform, and we can handle plus minus 5 inches of horizontal displacement and plus minus 2 inches of vertical displacement. In terms of payload, there are 4 actuators handling motion in each direction, and with a maximum force capacity of 300 kips. And the platform itself is 100,000 pounds, so we can typically hit 2.5 Gs of acceleration on some heavy specimens, even though it's a bit beyond the table capacity. We are IAS accredited to test IEEE 693 and AC 156 qualification specimens on the shake table. I'm just going to go over and show some videos of the tests we do instead of talk too much about what our capabilities are in interest of time. So this is one of the research videos, one of the research tests that was done in 2017. In fact, it's my test, part of my dissertation. It's a bridge bend 1/3 scale, which utilizes 2 hybrid recentering columns. The plots show base shear versus drift that's a major plot. The other plots show acceleration. So I'll go ahead and play it. So this one is earthquake 9 from a suit of initially planned 12. It's 90% scaled history of the Kobe earthquake from 1992. And you can see the flat shape response, which is typical of hybrid recentering systems. On to the next video. So I'll be covering mostly research videos to begin with. And then we'll go over to commercial service industry tests that we also do. So last year we also put a turbine body on the table. This was research but not testing the turbine itself, rather fiber optic sensors with Dr. Matt DeYoung at UC Berkeley. The interesting thing about this project is we typically don't use all 6 degrees of freedom in any testing, but this test did. So I'll just show a video. We do have a skylight, as you can see, and the specimen itself was sticking out like 30, 40, 20 feet above the table roof. So the specimen in total was, I would say, about 80 feet tall. So I'll just show a video of the yaw motion, or rather the pitch motion, which is not typically used in shake table testing. So UCSD shake table did show it in action, but typical research projects don't end up using it. But just a reminder, this is there. It is a 60 degree of freedom shake table after all. So it does not look a lot, but it is 0.7 degrees of rotational motion at a really low frequency. It was a sinusoid motion. And I'll go on to a next slide, which is a tiny home tested again last year by Professor Nema from SFSU. This is the second last motion done on the house, and you will see some destructive testing going on over there. So the specimen itself is an off-the-shelf, so to speak, house or shed from a place like Home Depot, for example. And the intent is to provide temporary housing after earthquakes. So I'm keeping the audio muted because it tends to get pretty loud when the table is operating. So I hope that's okay with everyone. So yeah, you can see the door opening and the walls of the unit coming apart. I believe this was a 2.2 scale motion of probably the Northridge earthquake. Next one, now I'll talk about some of the service industry work that we do. These are the main projects we end up doing in the lab. We typically end up doing 20 to 30 service industry projects on our shaking tables, to give you an idea of the turnaround time. This was a semi-research, semi-service industry project. The movement frame itself is a repeat frame, a reconfigurable movement frame, and the payload on the frame was a shape memory alloyed brace that is actually going to be used or already in use in a building on the main campus over here. So that's the main payload project, so to speak. Oh. So it does not look very exciting, but on the table itself, while it's running, yeah, I mean, it's somewhat fun to see. Although research projects typically end up not shaking the table really hard. And I will show in the next slide what commercial testing looks like. So this is one of the electrical switches, kind of tests that we do every year. We typically end up doing 3 or 4 of these every year for multiple companies like Southern States or MindCore or any other company. So typically these are done on behalf of facilities like PG&E in California, for example. So to give you an idea, the overall height of the specimen is about 25 feet. And when the switches open, it adds another 10 feet to it. And you can see the switches are open in this case. We also test bigger switches, and that is what the skylight is for, because the switches, again, when they open, they extend outside our building. So there is a video on all this, yeah, just to give you an idea of how loud it is. So even though the hydraulics are in a different building, it still ends up being pretty loud. So this one was a fairly okay test. This is an IEEE 693 history. But sometimes these insulators high up in the air do break and fall down on the floor and shatter into 1,000 pieces. So that is really exciting, and by exciting I mean not good for my heart. So that's some of the tests that we're doing on the shaking table. The second lab that we have is the structural testing lab, which is right next door to our shaking table. The big eye catcher in the lab is our 4 million pound UTM. I believe this was one of 5, and to give an idea of how old it is, it was built in 1932 and it's still functional and in use. So this is the main eye catcher. You walk into the lab, you will be just amazed by how tall it is. So it is about 45 feet tall from the base to the top, but in addition, there is also another about 20 feet below ground where the actual hydraulics are. Besides the UTM, we also have a strong floor and a reconfigurable strong wall. Although don't ask us to reconfigure it, it is probably a month work to just take it apart, and then resetting is even worse. It's not been done in my presence. We also have a frame mounted to the strong floor at the moment where we can drill and mount specimens if needed. We also have supposedly a 1D shake table, although we have not used this as a shake table in over the last 5 years or so. In addition, we also have a fleet of actuators for both static and dynamic testing. And finally, we have a self-reacting damping machine testing frame, which can apply loads up to 450 kips at minimum, probably can go up to 600 kips. Again, we have not pushed it to 600 kips in my presence. I've been working here for the last 4 years, but we have done it to 400 kips. Now I'll just showcase the UTM breaking a column. This was a column tested for University of Cincinnati in 2021 with Dr. Sharuz Baram and his student Elizabeth Mosier. There is sound in it, so brace yourself. So I don't believe this was a very high load test, maybe only 2 million pounds. We have broken specimens at 3.5 million pounds recently, And when that happens, you can feel it in the shake table next door, which is at least 100 feet away from this lab. We also provide platform for students doing research. For example, a student of Dr. Musalam, Juan Meriles, is actually developing a hybrid simulation platform which is simpler to interface with compared to the NTS Flex Test and the NTS software that you may be aware of and have used. And it is also intended to be much cheaper, although not as accurate as what NTS can do, of course. In addition, here is a test that we recently did on the strong floor and the strong wall. And again, I will say brace yourself, this is going to make you jump. It definitely did to me because I was pretty close to it and I did not like being there. Okay, oh, I've got the sound off, so I guess you got lucky there. So let me go back to the start. So in the actual testing, this is to give you an idea. The spring, this is a big spring, part of an array of maybe 20 springs used under a federal building, and the spring bar diameter itself is 3 inches, and the overall spring diameter is, I believe, 28 inches. My apologies. And this motion was actually a two-directional motion. We sort of built our own shake table using a strong wall in the floor, using sliders, and this test was actually replicating an impact loading on the building. So we essentially replicated not quite an earthquake, but an impact load on the whole building, and we actually have a really big impulse loads happening on the spring. Besides these projects in the 2 labs, we also do some educational outreach. So these are pictures from last year where we had undergraduate students visiting the lab to see the lab in action on one day, and on the next day we actually had grad students where we actually provided data to them from this repeat frame that they were supposed to use in their coursework. So I'll just show the repeat frame in action because this one is a pretty big motion in terms of showing the swaying of the frame itself. So again, there is no audio, but the shake table is pretty loud, so I left the audio out. This was only a one-directional shake because the repeat frame was configured with braces and not intended to move out of plane. Besides that, we also have some additional capabilities. We have a blast testing machine for ballistics testing, although recently a student had been testing them ballistically for glass panes. We also have a self-reacting small test machine in a room adjacent to the strong wall and strong floor. We also have a fire research lab, although it has not been used in I don't know how long, but we can bring it back up and running if there is any interest. We are planning to do some upgrades in the table in the coming years. Depends on if the university can give us some money, either loan or gift. Gift would be great. Or if someone from you is willing to come in and give us money. The current table is 20 feet by 20 feet. We plan to change the platen to 18 by 18, although the mounting area would be the same. We need to reduce the edges so that we can get more displacement capacity. Currently it's plus minus 5 inches. We intend to increase it to plus minus 12 horizontally and plus minus 4 vertically. We also intend to increase max velocity and also change the load capacity, acceleration capacity, and with the newer actuator fleet, hopefully better frequency response. And lastly, the table itself has an airbag to contract the platen weight, which we hope to replace with actuators instead, because the airbag does affect the frequency response a little bit. So here is on the left is the current configuration of the actuators under the table. We have a pinwheel configuration of the 8 horizontal actuators, which I have been told is a poor way of doing, or rather a poor configuration for a shake table. Although when it was built, obviously that was not well explored because it is a 50-year-old table, and with this table is, I believe, when MTS actually got its feet wet in building shake tables. So since then they have done a lot of research and development, so now they have better configuration, the one on the right, which is similar to the one under the UCSC shake table with reconfiguration of actuators. And yeah, the intent would be to have bigger actuators, a deeper and bigger shake table made of steel, which can hopefully do better work than what we do currently.